Okay, everybody, let's get started. We are in the operating systems course, and it is Monday again. And we are going to run until 12:30 today, because I have a meeting at 12:30. So we'll go from an hour and a half or so. More than enough time to cover what we need to cover for today. So today's topic, we are picking up where we left off last time, and we left off on mutual exclusion through operating systems. And that topic was from lecture 4B, and 4B was on inter-process communication. So we've covered the processes, we've covered threads. Now we're talking about, or I'm talking about, issues related to multiple threads running together, or multiple processes running together, and communication that happens between them. So what I want to cover right now is the concept of semaphores and message passing, which is how we're going to communicate directly with a process from another process. So far, just because I hate starting in the middle of a lecture, the beginning of this lecture talked about the concept of what inter-process communication was. I'm going to talk about deadlocks next, and then I'm also going to cover some classic problems. The one problem we've looked at already is the producer-consumer problem, where one thread is producing something and another thread is consuming it, and how a race condition might occur. And the race condition is, well, which one is going to get through the shared area, the critical section first, and whoever gets there first is going to change the value of what's there. And so we constantly have two processes that are in battle with each other to essentially perform the same task together. So they need to communicate so they can coordinate their efforts so we don't have this race condition. By definition, the race condition is the timing at which the process gets there first. Whichever process gets there first is going to be the one that wins the race. The one that wins the race is not necessarily going to be the best winner. So there's a chance that different executions might end up with different results. If you create a CP program to copy one file to another, and you use an inter-process communication technique with multiple running processes, like producer-consumer is a good model for this one. What will end up happening is sometimes you run it, the copy works correctly. Another time you run it, it's slightly wrong, like it's missing a byte, or it has one byte too many, or something. And that happens because of the race conditions normally. So that's one of the challenges with working with the producer-consumer model. I also went over some definitions I want to refresh your memory on, so we're on the same page for this lecture. The critical sections. So a critical section is anything that's shared between the multiple processes. So the contents of a file for a CP command, the contents itself in memory would be the shared variable or shared buffer. So we have bounded and unbounded buffers that we work with. The bounded buffer is fixed towards a certain size, and we can use the size of that buffer to control which process has access to it. If the buffer is full, we don't need to produce anymore, so the consumer can drain it all out, and vice versa. For conditions where it's empty, the producer has to produce for it. So we have issues with a critical section, meaning that we need to protect it. So that's where this word mutual exclusion comes into place, and it's a method for preventing more than one process to be in the critical region or critical section. Sometimes some books call it critical region, some of them call it critical section. I like the word critical. That's about it. I'll use region more than I will section because it's the critical region. And mutual exclusion is sometimes abbreviated as ME. I'll just say mutual exclusion. So you'll see it in the text, sometimes abbreviated. Critical section is what we're trying to protect. Mutual exclusion is the concept of only letting one process at a time get into that critical region. Why processes need to communicate? At this point, most people are thinking, well, can we just avoid all these problems by just having one process at a time running? And then we could go back to, let's say, DOS, or we could go back to batch processing, where we only have one process running at a time, and if only one process is running, and we don't have really the same user experience that we have today. So we could avoid all these problems by not running multiple processes simultaneously, but that wouldn't give us a very nice computing experience. So the higher degree of multiple processes running, the higher degree of multi-threading and user activity and user interaction you're going to get, because you're going to have multiple programs running all the time. In Windows, you have multiple screens that come up, multiple things happening in the background. So it's a very important concept, and we can't just go away with it. So we have to figure out how we're going to deal with it. To synchronize executions, to exchange data back and forth between them is kind of the issue. My ears started popping. As soon as I start lecture, my ears start popping for some reason. It's probably because my jaw is moving. So. All right, so rules for critical section or to form a critical section. These are sort of, oh good, it just cleared. These are sort of really good background things to remember. That no two processes might simultaneously be inside of the critical region or the critical section. That's the definition of mutual exclusion. No assumptions are made about the relative speed or the number of CPUs. So none of this stuff relates to how fast the computer is running or how many CPUs might exist. When we get into CPU processing, that actually is determined by, some of the CPU scheduling and processing is affected by multiple CPUs. But for inter-process communication, we don't really care about that. We don't also care about how fast the computer is running. It doesn't really matter. It's like when you start comparing algorithms. It doesn't matter how fast an algorithm, the speed of the algorithm running is not dependent on the speed of the computer. It's the algorithm efficiency itself in terms of what it's doing. So the same process applies. And also the processes outside of the critical region should not block other processes. And then no process should wait forever. That's called starvation. When one process waits and waits and waits because it can't get access to the critical region because another process is blocking it for some reason. So the starvation situation, by definition, when a process waits indefinitely, it's delaying the scheduling of the process in favor of another process. So the CPU is favoring other processes. So it's starvation. It's a favoritism. And when we look at CPU scheduling, which is actually our next topic, you'll see how favoritism is sort of a priority. It's something you can build in to make the system run faster, but it causes starvation. So it's what's good for us or good for the system is bad for the system at the same time. So, cause of this is a bias in the system scheduling. The solution is to implement some form of aging so we can avoid that. The other problem that we looked at, and by definition, but we'll see more examples today, is the problem of deadlocks. You need more than one process to deadlock. It's two or more processes that are waiting for each other. We also have this situation not on the slide called a circular wait. That's when one process is waiting for another process that's waiting for another process that's waiting for another, and it's all in a circle. So everybody's deadlocked. Causes a deadlock situation, but it's really a circular wait. By a deadlock, it doesn't mean the process can't run, it just means the process can't get into that critical region. So if the process can do other work, that's busy waiting. It's busy waiting and doing other work because it can't do what it needs to do. It'll never get done, but it'll do other work at the same time. What does that do? It eats up processor time. So it's kind of like people who constantly check the phone. You're busy, but you're checking. Is it there yet? Is it there yet? Is it there yet? Can I go in? Can I go in? But you're spending all your time doing that. It's busy, but you're not doing anything. So in the end, you just have to stop and start over again anyway if you're the process. So all that time you did was wasteful. Everything you did didn't accomplish anything. So it's kind of like when you start a project and you're working with a group and you spend all your time putting together this lovely outline and then the group doesn't use the outline or something. It's like wasted work. So busy work. Alright, so two or more processes are blocked waiting for an event that will never occur. Generally, A waits for B to do something and B is waiting for A. So both are not doing anything. So we also got into the concept of how to implement mutual exclusion, and we looked at a couple of scenarios from an application perspective, a hardware perspective, and then we stopped on the operating system perspective. So just to review this a little bit, just so we don't start in the middle here. If we do it from an application, then the programmer itself builds some method into the program. You will have an assignment for this course where the programmer, or you, will build mutual exclusion into the program that you're designing, and you're going to control it from your level. If you're an operating system, you're going to do it from a hardware level or an operating system level. Hardware level is nice, but you have to have the hardware. And how do you know what hardware you're going to have if you're the operating system? So if you can be built on specialized hardware like a MacBook, as an example, the Mac OS X is built for Mac hardware. We know what hardware is there. We could possibly put mutual exclusion into the hardware and have the specialized hardware for that. if we're a generic operating system running on generic hardware, we're not necessarily going to have the support for the hardware instruction. So we're going to do it from an operating system level. If we do it from an operating system level, that's what we're going to talk about next, with the semaphores and things, mutexes and things, to support and basically have the programmer do it, but use operating system services to facilitate the communication. So all schemes rely on some code for entering into the critical region and then exiting out of the critical region. So just the review from the application level, from an application mutual exclusion that's implemented by the programmer. It's hard to get it correct. Very inefficient because you have to build weights, or you have to build checks, or you have to build blocks into the system, which may not necessarily be the most efficient way of designing a program. You know, you're constantly putting in inefficiency, slowing your program down so that you can control what your processes are doing. So you're relying on some form of busy wait. So the process is testing a condition, setting a flag, looping until the condition remains available so that you can go into the critical section. And you're looping while it remains the same. And so going back to the producer-consumer, it's going to slow down the CP command. So if you have a CP command, which I'm talking about as a Linux or Unix copy command, taking one file, copying it to another file, usually at different locations. If you load it up into a buffer, the contents of the file, and then have a producer and consumer, one of them is writing it while one of them is reading it, theoretically it should basically run faster than taking the whole file, loading it up into memory, taking the whole file and copying it back out into a file, one at a time, sequentially. So the way you get around that is you put two processes in there. And then if you're doing the routine to check for the mutual exclusion, if you're doing it from an application level, then you're adding in checks. So one process is waiting, and then the other process is waking up, performing some work, and then it's waiting. And so you're constantly going back and forth. Well, there's time. They usually call it, in CPU time, they call it context switching. But there's time it takes to switch and to check between the processes. That slows it down completely. From one certain point, if you don't design it correctly, it runs slower. Copying a command with two processes, copying a file with two processes might actually take more time than if just one process did it from beginning to end. Which is the problem you run into if you don't design it correctly as a programmer. So a lot of people shy away from that kind of multi-processing, multi-threaded application development because it could possibly take longer than if you just had one process doing it. If you have hardware support for it, or if you have operating system support for it, it doesn't take as long. So you don't have to build in the busy waiting and the mutual exclusion in the program code. The best of all scenarios is the hardware. So you test and set. They're not checking for something in memory. You're not utilizing resources. It's a physical kind of check and a set on a hardware piece that's going to essentially be shared among all of the different processes that are running. So you're swapping the value, and you're setting a variable. You're checking the value of that variable. Advantages of using a hardware mutual exclusion scenario can be used with single or multiple processes with shared memory. Simple, easy to verify, can support multiple critical regions or sections. Problem, busy waiting is used as well because the process still has to check. If it's not checking something in memory, it's still checking the hardware. So you're still implementing some sort of a busy wait scenario to accomplish the mutual exclusion. And starvation is also possible. If one process is able to check it, set it, and then check it, set it, keep setting it, then you might actually have other processes that can't use it at all because it's starving. And deadlock is also possible, especially with priorities. If you have two processes trying to change the hardware simultaneously. So another one is to disable, another solution from a hardware perspective is to disable the interrupts. So on a single CPU, only one process is executed at a time, and you're constantly switching the value or disabling, enabling, without checking a value or without setting or using a buffered piece of memory or a variable. So concurrency is achieved by interleaving the execution, usually done by using interrupts. So if you disable the interrupts, then you can make sure that only one process is executing at a time, and the process can lock a system or degrade the performance greatly if other processes can't run, because it's constantly disabling the interrupt. So this is actually where we stopped. So we're talking about now, and we're not going to do it from a hardware perspective, we're not going to do it from a programming perspective, but we'll do it from an operating system. Linux and Unix have taken this approach. Windows doesn't do this approach. So in a Windows system, there's no OS support for mutual exclusion. All of it has to be done by a programmer. There's no hardware support either. But no programmer will do it because it's not required. It's better not to work with it, actually, because you don't have any control over it. Instead, the operating system is going to control its own processes and its own process scheduling so that the programmer really doesn't have to do anything but use the code that's available to them or use the facilities that are there. So if you're on a Unix or a Linux system, you have access to semaphores and message passing. So what's a semaphore? Well, Unix OS 2 actually supported it as well, but OS 2 I don't think is even around anymore. More advanced, incorporated into many operating systems like Unix. So a semaphore is a non-negative integer. It has two valid operations. It has a wait or a signal. So you have the kernel keeping track of the processes that are running, and you have the ability for the processes to send signals or semaphores or set semaphores so that the operating system itself, or the kernel, really the operating system is the kernel, is keeping track of which process can run. If you let the operating system do it, then it won't schedule a process that can't run. So you have more efficient CPU scheduling, you have more efficient memory management, everything across the board runs a little bit better. So a semaphore is a wait, blocks processes, they wait for another process to run. Then there's a signal, so there's a blocked process on the semaphore, then wake it up. So it automatically checks to say, well, who's waiting? Instead of the processes doing the wait check. So the difference is from an application perspective, you don't have to tell the process to keep checking. So it eliminates the busy wait. So the process is, can I run yet? Can I run yet? Can I run yet? No more of that. Instead, the kernel says, okay, you're done running. Okay, you can run now. So it signals wake up, sleep, wake up, sleep, wake up. And it coordinates like a traffic guard. It coordinates the processes for us. So there's two types of semaphores. There's the on or the off, or there's the counting. So we can do binary where we have only 0 or 1, or we can count to any non-negative integer value, 3, 4, 5, 6. It depends on how many processes we're going to schedule together to inter-process communication among themselves. If it's just two, it could be an on or an off. Or if it's a group of processes running, that whole group could be turned on or off. So the semaphores are on the operating system service level, and they're implemented using methods that shown already in terms of either semaphores that are hardware supported or semaphores that are memory or software buffered. So we're setting a value, and the basic difference is the kernel is keeping track of this. From a programmer's perspective, you could create a semaphore by using a system call, and you're going to use a mutex, and you're going to program using system call interface to this set of library functions that the kernel supports. Can only be done on a Windows, on a Linux or a Unix box. So most often the operating system disables interrupts for very short periods of time, uses hardware support, because you're designed to run on the hardware. If you're a Unix box, you're running on hardware that you've designed yourself. There's HP UX, there's Sun Unix, there's different varieties of Unix that are made for the hardware. There's BSD Unix that's made for Mac. There's a semaphore library on the MacBook. There's not one on a Windows because we don't have the ability to predict what hardware we're going to get, nor do we have the ability to predict from an operating system level how to let the user program its processes. Instead, we have the assumption that the operating system will handle everything. There's no user control over it, which is kind of an interesting phenomena. And there's pros and cons. I mean, it's like just because Windows doesn't allow the user to program with threads and processes, is that a good thing? It's safer. The user can't make a program that's going to do anything damaging. Much safer. On a Unix system, you could possibly create a program that's going to cause a problem. It's going to take the system down. And that happens a lot, actually, when you have a inter-process communication going on with multiple threads, and it's a background job running, and it's eating up all the resources. Or it's blocking other processes, so print jobs don't perform correctly, or something else happens. So there's more potential for problems. So going back to the producer-consumer problem, if we produced a solution using a semaphore, we get rid of all of the memory sharing between the consumer and the producer. So the producer would produce something, it would wait, put something in the buffer, and then signal, okay, I put something in the buffer. And then it would signal directly to the consumer to go out and say, well, okay, we're waiting, get something from the buffer, now signal, I got it, and go back. It's like people talking to each other, or two processes just communicating back and forth between the two processes versus using a piece of memory to, or the buffer itself. So the initial semaphore is a mutex. It's set to 1, and then we set it to 0. And then we go back to 1, set it to 0. So we essentially are communicating and signaling back and forth. You can run, you can run, you can run, you can run. It's kind of like a handoff. So one process hands something off to the other process, and what they're handing off is the change in the mutex. So it's okay. All of a sudden they're woken up. They're signaled to wake up, and then run again. Much more efficient than both processes checking memory constantly in a loop. So the looping is gone. So it runs a lot faster. Here's another example where we have 3 processes that are all sharing a resource. And now one draws an A, one draws a B, and one draws a C. And we implement a form of synchronization so that the output appears as A, B, and C. So process A runs, process B runs, process C runs. And then they signal to each other. So you guys, for people who are familiar with track, it's kind of like relay. You know, one person runs and they pass a baton to another one. It's probably not called relay, but I don't know. They baton passing, which is what you're doing with the mutexes. You're baton passing. So one process is going to, okay, here's your turn. Okay, your turn, your turn. It's a chain reaction. Much better way of synchronizing the efficiency. And you might think, well, aren't we making this serial? Well, we actually are making the whole thing serial when we start working with inter-process communication, because only one process at any one moment of time is entering into the critical region. Isn't that serial processing? So it's a better form of serial processing among multiple processes to all go in at different times and have them synchronize, essentially. Which is actually kind of funny. You can do the same thing with Java, and the word is synchronize. So you synchronize, or a synchronization, you put synchronize on it, all of a sudden the JVM is going to synchronize it. So it'll coordinate among all the processes so that they don't fight with each other. And that's how you could do multiple process running with Java, actually. So as I mentioned before, you can't do it with Windows operating system using C++, Visual Studio, .NET environment, but you can load Java on a Windows system and do your process synchronization inside of Java. So for those of you who are still trying to figure out how to do the first assignment and don't want to do it in C, do it in Java. It's actually easier because of the synchronize feature that you could put on a method, on a class. You just put synchronize on it and make it synchronize, and then go look that up on the internet to figure out how easy it is to make the processes run with each other. And everything is synchronized. So, and you might want to consider that for some of the other assignments as well. Programming in Java is actually pretty easy because the operating system is the JVM. The JVM has support for multi-threaded applications. So you're not working with Windows limitations. You're working with Java at that point. So, because the JVM is loaded on top of the operating system. So it's an operating system on top of an operating system, essentially. So let's see, we have B is equal to 0, C is equal to 0. We're going to synchronize, and we're just passing the baton back and forth between A, B, and C. You want to think of it that way. Changing the states, wait B, so draw A, signal to B, wait B, signal to C, and then go back to A, or wait C, signal to A, or draw C. So going back to the bounded buffer problem. So it's a bounded, this is not a bounded buffer. This is a semaphore, or a signal back and forth by operating system support. A bounded buffer is we're looking at the buffered information and we're binding our activity with our synchronization, reading and writing to that buffer. So we have that shared memory scenario going on. So we could do it with 3 semaphores if we wanted to and combine the process. So we need a semaphore mutex to have mutual exclusion on the buffered access. So on the access to the buffer, upon leaving or entering, we can change the mutex and then have the operating system support our entry in and out of the buffer. So we could have multiple threads reading and writing to the buffer, all doing it one at a time, serially, just the same as before. So we need a semaphore full to synchronize the producer and the consumer on the number of consumable items. So if the buffer is full, there's no need for the consumer to go into it anymore. And once the buffer is full, the consumer can't consume anymore. It's kind of like you filled it up. So that guy can just wait indefinitely, or hopefully not indefinitely, but it can wait until the consumer's done. And then why should the consumer stop after each one of them if it's full? So it's like an on, off, and full. It's like a 3 level instead of a 2 level on and off. So on a full condition, the behavior changes. So the processes don't have the busy wait of having to go, okay, I produced one. Should I produce another one? Should I produce? No, just go. Just produce all you want. And then consume all you want, because the producer can't produce anything right now. We also have the opposite, the empty, which says, we're done consuming, it's empty, so stop trying to consume, instead let the producer run. And then the producer can run completely. So what if the producer produces everything and then the consumer consumes everything? Is that faster than if one process produced and one process turned around and changed roles and consumed? It's relatively equal in time. So you don't want to necessarily run it that way. You want to design it so they're both working, but they're both working together. So it's kind of like how you have a group project, but only one person does all the work. So, oh, I believe it is attendance time. So let me pause the video. Okay. All right. So the bounded buffers. What was I talking about? Using more than one. So instead of an on or an off, we have, hello, we're back. And instead of an on and off, we have a full, an empty, an on or an off, mutex on, mutex off type of scenario. So what we're looking at in terms of the shared buffer is also considering the memory. So if we have a shared data, then the semaphore can be full, empty, or mutex, which is a 3-level on, off, or 1, or a full, empty, or mutex environment. So we can actually be more productive because we can stop the consumer from consuming if there's no room left to consume in. Or if there's nothing left, the consumer can stop. If there's too much, the producer can stop. So if we were to look at the source code that would be associated with the producer-consumer scenario with a bounded buffer, we'd have something like this. So produce an item, and then wait, and then we have a check on an empty, and then we have a check on a mutex. So instead of just being 1 or 2 mutexes, there's 3 to check for different scenarios. Are you the one that emailed that you were running late? You just missed the attendance guy. Oh. You did the attendance?
Yes.
Oh, okay, good. You didn't email. You were sitting in the back then. Weren't you just here this weekend?
Yes.
Yeah. Isn't this kind of a long weekend? Notes on the bounded, and I did go home and come back. Although I feel like I've been here for like the last 3 days straight. I have, actually. Notes on the bounded buffer solution. Yeah, my apartment is on the 2nd floor. No, it's on the 3rd floor. We don't have a 3rd floor. The notes on the bounded buffer solution here. The remarks here from the consumer point of view. Putting a signal empty inside of the critical section of the consumer instead of outside has no effect on it, since the producer must always wait for the semaphore before proceeding. So depending upon where you're putting it, you may or may not have an effect in terms of the end result. The consumer must also perform a wait full before the mutex, otherwise the deadlock is going to occur. So in the best of all worlds, it would be nice to be able to create a scenario where if the producer can't produce anything, he also knows not to check. However, where you're putting it is going to be either inside of this critical section or outside of it. Depending upon where you're putting it, the producer may still have to check, and the consumer may still have to check, regardless of the best plan you put together. So the idea is that using semaphores is difficult art, and that's the concluded thought on this. It's almost as difficult as doing it from a programmer perspective and using a shared buffer without using semaphores. So it is probably one of the most, using semaphores in the system libraries, system interface calls to the mutual exclusion that the operating system provides is probably as difficult as doing it from a programming perspective. So unless you're a systems programmer, you're probably not going to play around with that much. You're just going to have one process in your program run. And this is when you're creating your program, you're writing an application to run at the application level. How many processes are you going to have in there? Most people will just go with one because of all, you equate all the other problems that might exist, and you figure out, calculating out, how much is it worth my effort to create multiple processes to do this? Most likely it's not going to be worth your effort. So what is deadlock? Well, deadlock is when two or more processes are waiting for something and neither one of them can produce. It was actually kind of funny on a multiple choice. Actually, it was a multiple selection where on it was a final exam for this course actually a couple years ago, about a year ago or so. I put on a question on the exam, and everybody's listening now. The question on the exam, and I probably will do this again, it says, how many processes do you need for a deadlock at a minimum? And the choices were A was 0, 1, 2. I said 95% of the class picked 0 or 1. It's like, oh, you need one process. No process. How are you going to have deadlock without any processes running? It's like, you're not going to happen. How are you going to have it with one process running? Never going to happen. You need 2 or more processes for a dead. So now you're not going to get that one wrong. You guys are sitting here, you'll get that one correct. I like to put that one on there because, actually, I like to put the questions on there that are kind of humorous because I have to grade these things. So when I look at it, I want to, I get a laugh out of it. It's like, wow, 0, 1, that's great. Or I'll put something as an answer. It'll be like, instead of semaphore or mutex, I'll say significant or mutotics or something, or some misspelling of the word or something. So it sounds like something else, and then they'll pick it because you'll see the M. Oh, that must be the right answer. It's called a mutotics. What? It's called a mutation. Oh, okay. So what is deadlock? So process deadlock and system deadlock. System deadlock is the blue screen of death you used to see in Windows. That's a system deadlock. What does that mean? Memory got corrupted. Usually the system deadlocks in Windows are caused by memory corruption. Because that blue screen of death used to have memory addresses on it. If you remember the older versions of Windows, it pops up and says, error at address blah, 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 blah. And it meant nothing. So the errors went away. They repressed it so nothing got printed to the screen, but you still saw the blue screen. So, and then sometimes you rebooted your computer and you still saw that blue screen. It's memory related normally, but it's a deadlock. Something can't run. So a system is deadlocked when one or more processes are deadlocked. It causes the system to deadlock. So a process is deadlocked when it's waiting on an event that will never happen. So that's when you see the screen that comes up and says waiting, waiting. You get enough of those screens and Microsoft Word deadlocks. Applications can deadlock, operating systems can deadlock, but really the core of the problem is a process is deadlocked, and it's caused one of those other situations to occur. Necessary conditions for a deadlock. Well, you have to have mutual exclusion occur. In order for the problem to occur, you're going to need to have a mutual exclusion, and you're going to have a hold and a wait, perhaps. So a mutual exclusion is when you have shared resources that are used mutually and in an exclusive manner. Well, what's the biggest shared resource you have on the computer system? Memory. Memory is a shared resource on your computer system. It's shared by all of the applications that are running, including the operating system. When you have a shared resource like memory and you run out, you get deadlock. Because either you get swapping because you're loading something into memory, taking something out of memory, loading it into memory, taking it, and you're doing all your work, all your processor time is swapping memory back and forth. that could cause a deadlock, actually. The window that comes up and says waiting, it's not in memory. It got swapped out of memory, and the shared resource is essentially full. You've filled up your memory. So what's going to happen is that system is going to sit there and the window until you close something. So if you want to get rid of a waiting screen, start closing programs down. Don't load as many programs. You're never going to have a blue screen. Actually, you don't have the blue screen anymore anyway. Instead, now you just get the system rebooting. Occasionally, the system will just hose. No more blue screen because that became everybody's joke. So now everything just suddenly stops, and then you have to press down and reboot the system. Or the system itself will reboot on its own. So no more blue screen. But it means the same thing. So the memory is the shared resource in the operating system that generally causes a deadlock, and it's usually a resource that's scarce. So you could possibly load on a lot of memory, buy extra memory, and your system will run a little faster because it has fewer hold weights. So the processing of a hold on to a resource when it already have while waiting for allocation of other resources, and a hold wait, it holds on to one, waits for another. This is what programs do. It needs so much of memory. It gets so much, so it allocates so much that it has access to, and then it waits for the rest. But the rest isn't going to be available until something gets closed. So start closing windows and you'll notice how fast other windows that are in waiting will actually clear up. So people find that with Microsoft Office all the time for some reason. Well, you think about Office. You have a Word program. You're loading up a Word file. People put graphics in there, multimedia in there. Those files can be pretty big, pretty heavy. And the heavier it gets, the more memory it's taking up. So, long story short, you got 5 or 6 of those running because you got different copies of it perhaps. You're going to deadlock occasionally with that. Necessary conditions for a deadlock. Well, we have no preemption. So I mentioned preemption at the beginning of this lecture about last week or so. Preemptive versus non-preemptive processes. So a resource cannot be preempted until the process releases them. To preempt something means cut it short. Go over and knock on the door. Hey, you know what, process, stop running. Stop a process from running. You're holding on to my resources. Get out of here. Well, most operating systems aren't going to allow you to do that. You have to kill it yourself. So the user can go press Control Alt Delete, bring up the task manager, look at all these processes that are in there, and just start killing processes. That's a preemption. And a non-preemptive, the resource is never released. So we have a circular wait that happens. So a circular wait is a chain of processes existing that are holding on to a resource and waiting for other processes to give up their resources. So the classic circular wait scenario is what they call the dining philosophers. So the dining philosophers changed over the years, but it was a fork and a spoon. Now it's 2 chopsticks. But originally it was a fork and a spoon. You had an odd number of philosophers who were dining around a table eating spaghetti, and an even number, if I remember this, of resources. So you were 1 short. So, or was it the other way around? I don't know. Long story short, in order for a philosopher to be able to eat, he has to have a spoon and a fork. So if everybody picks up the fork, then nobody can pick up a spoon. So somebody has to, only one philosopher can't eat while the rest of them are eating, but they're all trying to eat at the same time. The problem scenario is an upcoming slide, but long story short, if they're not preemptive, they're not giving up anything. They're just going to hold on to one and they're waiting for the other, but everybody else is waiting for it too. And only, a certain number of people can do it. They cause everybody else to wait, causes deadlock. So to preempt it means, oh, if I don't have both, put it down. Stop it, put it down, start over again. I stop and I start over again. That frees up the resource. It causes somebody else to be able to run. And then eventually everybody can eat by somebody putting something back down. It's somebody walking away from it, essentially, not causing it. So no deadlock situation. If you can prevent at least 1 or more of the necessary deadlock conditions, then you don't have a deadlock and you'll never have a deadlock. It's kind of impossible to prevent everything from happening. Deadlock is a known problem. So here's an algorithm. It's called the Ostrich Algorithm. Actually, like the ostrich, when they get scared, they put a big hole and they put their head in the sand. And then they wait for the fear to go away, and then they pull their head back out of the sand. So pretend like there's no problem. Then you don't have to deal with deadlock. That's actually what most operating systems are doing now. Because what are you going to do? Constantly check every single program that's running? The checks to prevent deadlock prevention is time consuming. The time the operating system is spending to prevent the deadlock is time the consumer, the user, can't do anything with. So they can't run a program, they can't do anything. So you want to maximize the efficiency for the user, minimize what the operating system is doing. You take this approach, you prevent it from happening, hopefully, and then pretend like it's never going to happen. And then when it does happen, the user can reboot the computer. The user can just start over again. So how many times does it happen? Not too often, actually. Not as often as it used to happen, because the system is designed now to prevent it. So you can detect it. When it gets detected, deal with it. You can prevent it from happening and hope it doesn't happen, or you can just simply do nothing and then wait for it to happen, and then when it does happen, you can try and recover from it, or you could not recover from it at all. So it's reasonable if deadlocks occur very rarely. If you don't get too many deadlocks, you got a lot of memory, you're not going to worry about checking the deadlock on the memory anymore. So deadlocks occur very rarely, and the cost of prevention is high. It's going to cut down on your efficiency. Then you can take this approach and just forget about the problem. It's not going to happen. Unix and Windows takes this approach because it's easier not to deal with it than it is to spend the resources. The trade-off is between convenience and correctness. Are we creating a reliable operating system? No, because it could possibly fail. If we're creating a reliable processing system, we have to detect deadlock because we have to be running. If we're talking about an operating system that runs on a heart monitor, you know, this heart monitor is for patients. Let's say it's an embedded bioelectronic device that controls the pumping or the regulation. Do you want that to deadlock? It's kind of like this, well, that's what happens in humans. They have heart attacks. It deadlocks. The patient's probably going to die. So you're going to put something in there to make sure it doesn't deadlock, and then if it does deadlock, it's going to self-recover. It's going to reboot itself. It's going to fix itself because it can't afford to not work. It's like pumps for regulating water, for natural resources. For things. Do you want a bridge not to work? You know, no one's going to be able to go over the bridge. You know, so you want it to reset itself to prevent it. So there's ways of handling the deadlock if you're not an operating system and you don't necessarily want to deal with it. Windows can die. It dies all the time. Windows can just die. In fact, the longer you keep your program running, the more likely, the longer you keep your computer running, your operating system running, if you have Windows, the more likely you're going to have a deadlock. It's just a matter of time before the thing deadlocks. And then you just reboot it. No big deal. It's not a heart monitor. So if you're going to do it, and you're going to deal with handling it, the deadlock prevention, detection, avoidance, and then recovery are your stages of deadlock dealing. And if you're an operating system and you're a critical operating system, because remember on day number 1 I told you that a heart monitor is an operating system. An operating system on a computer is an operating system. A microwave oven has an operating system on it. If you're a microwave oven and you deadlock, you know what it does? It just turns itself off and turns itself back on. Most hardware appliances with operating systems like a printer, the user is just going to turn it off and then turn it back on. And then hope that maybe it doesn't run for too long. Which is why in the old days people said, just turn it off and then leave it off, which is what we do with our computers now. If you turn your computer off at the end of the day and then in the morning turn it back on, better performance, less deadlock is going to happen to it. Is it better for the hardware? There's so much controversy with that. Nowadays the hardware is so strong it doesn't really matter. Or a lot of people would sleep it. If you sleep it, it means it doesn't run. Same kind of concept, except for occasionally you do have to reboot it if you sleep it all the time. So deadlock prevention. Remove the possibility of the deadlock. Make sure it just never happens. Occurred by denying one or more of the following conditions. So we're going to enforce mutual exclusion. Can we share everything? We can designate, and this is what operating systems actually do in terms of prevention. Certain memory is only accessible by the operating system, and certain memory is only accessible by the user mode. So that's what Windows does. It takes up, in fact, the current version I believe takes up 2 gigabytes of RAM. That's not accessible to the user, which means you got to have 4 to 6 gigs on that system, or 8 gigs, in order for you to actually have a lot of space and user space. So think they're not giving you too much right out of the get-go with the minimum requirements that are set. So you have to actually add some to get some. But yeah, we're going to exclude that. You can't use that memory. They also do it with video RAM. So if you have shared video RAM and that's the shared resource that you're looking at and you're using main memory for that, your DRAM, you got 2 gigs on the system, you really only have 1.5 gigs, because half of it is totally excluded from the operating system and it's only used by the video RAM, or the video processor. So that's a way of doing it. You totally mutual. Don't share it. Don't share it. You don't have to share it. And I'm using memory as an example because that's the resource on a desktop computer that is deadlocked constantly. You can also create deadlock with a CD-ROM drive real easily. Actually, you just put a bad disk in there and the disk doesn't ever clear. So all the applications that are using it aren't going to work. So what normally the user will just pop the disk out or reset it or reboot the computer. Ports, the network doesn't normally deadlock. So the only thing that deadlock is the main shared resource is that memory. Memory is going to deadlock. Cache deadlocks. Cache memory will deadlock as well. Any form of memory. Remove the hold and wait. If we have a hold and wait condition, we're going to have a problem. Or the non-preemptive concept. Don't preempt it. Most I/O is not preempted. We can't preempt it. If we preempt it, we destroy the memory. It's like having half a file loaded up in the memory. Not going to work. We have to have the whole file. So we're going to wait for the whole file to get there. And then also circular wait could be something that could be prevented. So denying the hold and the wait, in terms of the implementation, a process is given a resource on an all or nothing basis. That's how your CD-ROM drive actually works. When you're writing a disk, that disk is going to run. And you try to stop it. Not going to stop. Pretty hard to stop it. It's not going to stop. You can't, even the user can't preempt it. Why do you want to do that? You're going to destroy it anyway. But if it was a mistake, forget it. If it's already started, it's already trashed. The disk is bad. So you're going to throw it away anyway. But maybe you don't want to waste your time sitting there waiting for it to run. While it's running, it's going to block the memory that it's using. It's going to block everything, which means your entire computer is going to run slower. Same thing happens with the USB drives, actually, which is why you never want to boot a system from a USB drive. Although it works, it's great, but all your I/O ports on your computers are normally blocking I/O, which means when it's working, it's the only thing working, which means your entire system's going to run slower. You're reading and writing through a bus rather than through an IDE channel or a SCSI channel, which is faster. So you're going through a slower channel to begin with, plus everything that's happening is blocking on that USB drive. So the memory's blocked, it goes back and forth. It's a hold-wait kind of block until it's done thinking. Then it's going to release. So it's going to run slower just naturally because it's an I/O device. Which is why you take the same concept, that SD card, or you take the SD card port blocks, the USB blocks, but you take the same memory and put it on the board in an SD drive, solid state drive. It's the same concept, it's the same memory, but it runs like 20% faster than it would if it ran through a port, which is excellent, you know. Anyway, long story short, I'm not talking about hard drives today, but it's because of the blocking and the holding and the waiting, and the blocking causes a hold and a wait. Holds, waits for something to finish. So either process gets all of its required resources and proceeds, or it gets none. So it can't get half and waits. You can deny the hold wait. The advantages are it works. Just don't let it hold and wait. Reasonably easy to code. Problem is it wastes resources, and that's the problem that we get. So there's a resource waste and a possible starvation. You get this actually all the time with devices. In fact, most people just pull the device out, put the device back in, because sometimes you will get it when you put the device in, it won't pick up the device. You go, what's wrong? It's not reading my USB drive. Well, because your resources are not available to load it, it's not going to be loaded. There's no memory available to allocate, to attach it, and to make it part of the file system, so it's not going to do it. So you pull it out, put it back in, and they go, okay, now it works. So it's starvation is what you're getting. It'll sit there. Sometimes it actually will break from starvation about an hour later or so, or a half hour later. Or you turn down something, you turn off something else, and all of a sudden, oh, look, my USB drive is showing up. Actually, classic test is put a disk in your CD-ROM drive and use that if your CD-ROM is off of the same port, off of the same path, it'll block. And so you put the USB disk in and it won't read it until your CD-ROM drive takes a break. So it depends on the path, depends on how the board is how the motherboard is actually setting the I/O ports, and because some ports actually block other ports at the same time as well. Like it's hard to read from two disks. If you copy files from one disk to another disk on a SCSI channel and you're going from one channel to another channel, slower than if you go between one channel and only one channel. You copy it from one section to another section on the same channel, faster, because you're not blocking. So it's the blocking that slows it down. Has nothing to do, it's the same routing, it's the same distance from the CPU, it's the same speed. It has nothing to do with the speed. It's the operating system's control of that port which is causing it to block. And the blocking is a hold wait, and the hold wait is what we're trying to deny. If we deny the hold wait, then we won't get starvation. Oh, we'll get starvation, but we won't get deadlock. So one of them, you know, and on one hand you could avoid deadlock, and at the same token you can introduce starvation into the system. And starvation is that waiting. What are we waiting for? You know, so we're waiting because we're blocking. So you can deny the non-preemptive. So in an implementation, when a process is refused a resource request, it must release all of the resources it holds on to and start completely over. So you're not going to preempt it, or you're going to preempt it. Instead of a no preemption, you're going to preempt it. Which means you can't run, get rid of everything you have, get out of memory, go away, come back later. Which is what the user does when it takes the disk out, puts the disk back in, turn the computer on, turn it off. Resources can be removed from a process before it's finished with them. So in a non-preemptive, you can't remove the resources. In a preemptive, you can remove the resources. You can stop it from running. Advantages as it works. Also possibility of better resource utilization. Only resources that are able to finish, only processes that are able to finish can actually access the resources they need. Problem, cost of removing a process's resources. You're halfway through reading a disk. What are you going to do with the memory? Save it? Because you're going to start it back up again in a few minutes. Do you want to start over from scratch? Or you've wasted all the time reading half the disk. Now you're going to throw it away and start all over again. Not too it's time consuming. Not good. It's not good. Also, you have too many overhead buffered information and stuff to save about the resource. And the process is likely to lose work that it has done. How often does this occur? A lot. You get half done. Oh, do it again. Do it again. Happens when you're actually copying from disk to disk. Sometimes the copy works, sometimes it doesn't work. Depends on how often you back stuff up, how much you, and then you end up just having to start over again. Tape drives cause that problem a lot. You see the backups never work. You should always check the backup. Actually, always check to make sure your disk got written correctly as well, because if it got preempted, it probably lost everything. Possibility of starvation as well. Denying a circular wait makes a lot of sense. However, Windows doesn't do that. That's when you get processes where they block other processes. Internet Explorer does this all the time, actually. You can look in the Test Manager and you got 25 Internet Explorer windows. Where did they come from? It's just a circular wait. It's like, oh, you double-clicked on it and it was waiting for the previous browser version. This is the older browser, and I don't know if it still has this problem. It was waiting for it because that's a multi-threaded program, and so it's waiting. And then, okay, let's open up another instance, waiting, open another, waiting. They're all waiting on each other to close down. So you get 50 of them in there. And all you have to do is go in there and start removing the people out of the queue, get them out of the circular queue, and then suddenly it'll start working again. Actually, I just have a tendency just to select them all, delete them all, and start load it up fresh again. Because you created a circular wait with that. You didn't do it, the operating system did it. So it felt it had an entry for it, and it didn't want to load it again, but it loaded it again, and it's waiting for the first one to come back and say, hey, I'm done loading. and it never comes back. So in terms of the implementation, the resources are uniquely numbered. So we don't have one, oh, we're loaded. Oh, yeah, you're loaded. Oh, loaded again. We're loaded. We're loaded again. Loaded again. So we have load 1, 2, 3, 4. The way they got around that actually is they created tabs, which is why the current versions don't do that. Firefox does that. Tab 1, tab 2, tab 3, tab 4. And then when you close it, do you want to close all the tabs? What you're really working at is 4 different versions of the same browser being loaded, but it's nested and it's numbered. It's numbered by its tab order. But you don't get the tab order numbering. If you got the tab order numbering, then you could go into the task manager and get rid of the sub ones, but you can't. You have to get rid of all of it. So it's the design of it. That's a multi-threaded application, by the way. So processing can only request resources in a linear ascending order, and thus preventing circular wait from occurring. So give everybody a number. Problems with this, it works, is the advantage. Problems with it, resources must be requested in ascending order of the resource number rather than as it's needed, which means you got to open up a new tab. You have to introduce a tab concept or something so you can have a numbering system. And the numbering must be maintained by someone and must be reflected in every addition to the operating system. Well, yeah, the application has to keep track of its own numbering and its own tabs, which actually makes it run slower because it has to keep track of all that memory associated with all the multiple windows that's opened up. So it slows it down a little bit. Difficult to sit down and just write code for this. That's a very hard thing to program, actually. Which is great that we're seeing some of it out, and they've experimented with a few different versions of it. So I like that better than like the windows that show up and you click on one of the windows and it opens up a new tab for you. So it's different. Or you could do avoidance, allow the chance of deadlock to occur, but avoid it from happening. So design the system so you can avoid the possibility, if possible. So you check whether or not the state is good before you try something. Well, that's going to slow your system down. You end up in a deadlock situation if you don't check it. So you check the state and see if that's something that's going to happen. If you're a bank, that's something you might do. So banker's algorithm, which is the technique for deadlock avoidance, actually. Each process has a loan and a claim, and then there's a maximum need that's associated with it. The loan is the current number of resources held. The maximum need is the total number of resources needed to complete. And then the claim is the maximum minus the loan amount already. It's kind of like your checking account. It's going to check your balance before it gives you anything. It's going to prevent a deadlock from occurring. It's going to prevent a problem. Which is actually how they're supposed to be basing interest rates and late penalties. Not to be on the bank side, but if you actually pay something late, it costs the bank money. So they initiate a late penalty to compensate for how much they're losing because they're short the resource. If they're short the resource, they can't loan it out to somebody else because the bank is a shared resource. It's so much money, and you have so many people borrowing, and at any one moment of time, they're on a schedule, they're supposed to be paying it back. And they're paying interest in for the cost of borrowing it. So, because the bank's going to make money. So if you're late, oh my God, you've messed up the schedule. If you messed up the schedule, you're going to delay somebody else from getting a loan. If you do that, then the bank's got to put more resources in, or the bank has to figure it out. So there's a penalty to compensate for that, because the cost of the money has now gone up. And so their revenue is going down, so they're going to charge you for it. That's the late penalty. Or the overdraft, the cost of the overdraft. So not to be on the bank side, but originally the design of that penalty was to compensate for their extra costs. But a lot of people think, oh, they're a bank. They got tons of money. Why do they need to do that? Why do they have to charge me overdraft fee? It's policy. So we have customer 1 and we have customer 2. Customer 1 needs $800. Customer 2 needs $600. The present loan amount is $410 and $210, and the claim is $390 and $390. It's the same claim. So suppose the total bank capital is $1,000. We can't do both. So current cash is $1,000. It's only $380. We can't even do either one, actually. We have to wait for someone to pay something back. So release a resource so we can allocate the resource. Here's the assumption. Establish a loan ceiling. Isn't that what the credit card companies do? It's a loan ceiling. You have a limit, credit limit. It's the maximum need for each one of the processes or each one of the people borrowing money. And the maximum need is less than the total number of resources available or the capital that the loan company or the credit card company is able to loan out. So total loans for a process must be less than or equal to the maximum need, theoretically. So the loan resources must be returned to the bank in a finite time, which is why you have the scheduled payment. So you're on a 30-day cycle, or you're on a 15-day cycle, depending upon your loan repayment schedule. So it's a finite time for the algorithm to work. So here's the way the algorithm works. It's the banker's algorithm. Naturally, you probably have figured out why they call it a banker's algorithm. It kind of applies towards things outside of banking, though. Search for a process with a claim that can be satisfied using the current number of remaining resources, i.e. tentatively grant the claim, one that's possible. Work with the ones that are possible first, so which is going to be the lower claim. That's why it's always easier to get smaller amounts of loans than it is to get larger amounts of loans. It's more possible. If such a process is found, then assume that it will return the loan resources, let them borrow the loan. Update the number of remaining resources, repeat the steps for all processes, and then mark them. And do not grant the claim if at least one process can not be marked. So you check all of them. It's kind of like how people pay bills. They go, I have so much money. If I pay this one, this one, and this one, and this one, they'll all clear. This one over here is a problem. We'll put him over here for right now. We'll wait for the next check to come in, then we'll pay him later. So you schedule it out so you can accomplish as many processes as possible, which is what we're doing. We're trying to pay as much as possible on time. And then we take the penalty, or we starve the other process that's not doable. So we try to mark as many as possible. In terms of the implementation, the resource request is only allowed if the result is safe. So you're not going to take this one over here or this one you're waiting because it's too big. If you wrote that check to this guy over here, all the other ones are going to fail. Not safe. Not a safe situation. So the system is always maintained in a safe state, so you have a positive balance, and so eventually all requests will be filled. It's the order that you're interested in. So banker's algorithm works with the order of the processes, and it's a priority-based algorithm, which is what we do when we pay bills, is priority-based. If this one's not due for another 2 months, you're not probably going to pay it right now. You're going to wait, so because eventually you're going to have to pay it, but you got the resources to accumulate by then. Advantages: it allows the jobs to proceed when a prevention algorithm wouldn't. So we avoid the deadlock by adding priorities. And the deadlock in this particular case is when all the money in the bank has run out and we have zero resources, all those bills aren't going to get paid. And all those people aren't going to be able to borrow money from the bank. And it's a deadlock. The problem with it requires there be a fixed number of resources. That's what happens with people's finances. So you talk to your average undergraduate college student who's managing finances for the first time in their life, and they have their first checking account. They don't think about what happens if my car breaks? Uh-oh, wasn't planning for that. And then you have all the bills set out, but all of a sudden you have, oh, medical bill. Oh, what? Car repair. What? Student loan. Oh, what? Textbooks were more expensive than I expected. You have all these unexpected resources that come in, and then that's the problem with the algorithm. It doesn't work. The algorithm won't work unless you plan for the unknown, which is why everybody plans for the unknown. You know, they save money for the car, they save money for the this. But you don't get there until you realize what that's going to be. So it's natural, actually, for people just starting out. Young people have that problem, and then they learn, oh, the unexpected. What happens if a resource goes down? What happens if you lose your job? Uh-oh, no resource anymore. What am I going to do with all these bills? Does not allow for the process to change its maximum need while processing either. So you realize, oh, you know that my budget's good except for I really need $100 more a month, but I can't do it. I don't unless I get a second job. This is the second job scenario. This is the job going away scenario. So, which is kind of an interesting. So, banker's algorithm, you won't forget it. Just relate it to your own personal life. So, we have other classic inter-process communication problems. The readers and the writers. We also have the dining philosophers, as mentioned before. So the readers and the writer models the access to databases. It's the read and the write. It's the block and the write, open it to read it, open it to write it, block it back and forth. So when you study databases and you want to build a database, it's the reader-writer process. Because the databases have multiple processes that are running simultaneously. Dining philosopher models the competing for exclusive access to a limited number of resources or I/O devices. So dining philosophers really talks about the I/O and the system. And then the sleeping barber problem models queuing. So you're gonna program with the sleeping barber problem actually in one of the assignments coming up. Next week I'll go over the assignments that are coming up past the first one. They're just different scenarios. There's a couple of different scenarios. This one is the one where you're waiting for the instructor during office hours. Models queuing in a situation where we have multiple person at a help desk with a computerized call waiting system for holding a limited number of incoming calls. And you're all waiting. So you're waiting because the barber is sleeping. So the reader-writer problem that mimics the databases. Any number of reader activities and writer activities are running. Imagine access to a database. Any number of people of the EMS, any number of people could be logged into it, and they could be doing something, posting an assignment, reading a lecture, or doing something. At any time, a reader activity may wish to read data. At any time, a writer activity might want to modify data, might want to modify something. Any number of readers may access the data simultaneously during the write process. If you're working with a database, you're updating a table normally. During the write process, no other reader or writer may access the shared data. So if I'm the teacher and I'm running a report of who's turned in the assignment, but you're turning in the assignment while I'm running the report, there's a problem. The number's changing. So there's the synchronization between the reading and the writing that happens. Actually, personally, I think that's why we have some issues with assignments, especially at the end. If you imagine all the problems with the EMS happen at the end of the term when everybody's uploading assignments. So if you wait till the busy time, you're going to have a deadlock situation occurs where two people are uploading simultaneously and the table's trying to be updated, but it's only going to be updated one time. So your assignment is going to wait, and if it waits too long, it's going to time out perhaps on the database, and if it times out, then it's going to tell you that it uploaded it, but it's not going to upload it. Or it's going to upload it correctly, but it's not going to be reflected in the database correctly. Which, you know, it sounds like a shared resource issue. And it's only because we have too many writers simultaneously. And there's something with the application level that's interfering with the update, is what I'm thinking. So, and the problem actually is kind of classic. It happens with shopping carts all the time. When you go ahead and you order something, it comes back and says, oh, sorry, there was an error. How could there be an error? Well, the EMS should come back and say, hey, there was an error. It doesn't do that, though. But it should go back and say, hey, there was an error. There's an error because it didn't update. The table is locked. Too many people were trying to write simultaneously, and it couldn't synchronize it. So readers and writers with active readers, it's okay to read something because it's not changing. So we have a reader who is reading. It can enter into the critical region. Here's the access to the database, and here's the scenario. Reader can come in and read all he wants, except for the stale data. So if you're reading something while something's being updated, you're reading an old copy. And then whatever's being updated is changing everything. Then you got to stop reading and reading again. You have to load it up again in order to refresh. So the writer writer must wait while reader is entering in. Reader has to wait for the writer or be signaled, hey, something changed. Would you like to update it? Or have the system itself update on all the writes. So reader's not as much of a problem as the writer when it comes to the database access. So with an active, this is here with just the scenario itself with active readers. With active writers, the reader waits until the writer finishes. So the writer comes in, writes to the database, all the other writers should wait, and then the reader comes in and reads after hopefully after the write has occurred. You study databases and you look at transaction management, and that's what you're talking about, is the reader-writer process synchronization issue, because it really is a reader-writer scenario that we're working with. So should the reader wait for waiting writers? Should readers wait for waiting writers? Man, maybe not. That's a circular wait. You're waiting for a writer who's waiting for a writer who's waiting for a writer, and you're a reader. So maybe you can just open it up and then be signaled, hey, it's changed now. Because when is it really going to change? If you think about readers, you're going to read it, you're going to wait until everybody's all done, or you're going to read it in the beginning. So the reader must have to wait. The writer must wait until it enters when all the readers leave. Is that going to slow down your database? So you can't do that. You can't apply a reader-writer out of stock where everybody waits. Instead, you have to synchronize everything. So you have updates that occur. Most banks take everything in during the day, and then at night, when no activity is occurring, everything's synchronized. So they have an algorithm that will synchronize all the credits before the debits. There's a rules that actually put into this algorithm. So if you go into the bank and you deposit cash, that's gonna post to your account first, and then you write 5 checks, and the 5 checks come in. Well, that's gonna come in second. Every single one of the reads and the writes is synchronized, and it happens sequentially in a batch process at midnight when no activity is occurring. If it happened during the day, you'd have problems with readers and writers, and the system wouldn't work. Could you imagine all the ATMs and everything going on? And every bank, still even in the year 2013, nothing posts till midnight. And they always say midnight, but it's really like sometime between midnight and 3 or 4 o'clock in the morning, because the whole process takes 3 or 4 hours. Because you're looking at an entire day's worth of activity, and it's networked. So you're looking at 3 or 4 hours of updating that database from everything that occurred. So by 6 o'clock in the morning, or 3 or 4 o'clock in the morning, your balance is reflected by it. So, which is actually kind of funny, because if you ever check the online system, some systems actually go down. It won't let you read it. So you call in, you wake up in the middle of the night with a panic attack or something. Oh my God, I think I have a negative balance in my account. You call your bank up, and sorry, the system's down right now. The system's not really down. It's in maintenance mode. It's updating itself. It doesn't know what your balance is yet. You're thinking faster than your account is thinking. So, all right, I'm going to end actually at this slide because I have a meeting I need to go to. And so as I mentioned at the beginning, we're going to end class at 12:30 today, and it's 12:28, so I got pretty close. So next time, somebody remind me, we'll start in with reader-writer problem, slide number 54. And then next time, we're also going to start in with CPU scheduling. So we just have a little bit. See, once we learn about threads and processes and how to synchronize them and the way that they're supposed to run, then CPU scheduling makes a little bit more sense, because CPU scheduling is making these guys run. And so we have the cues and the techniques for scheduling the running of these processes so they can synchronize their work. So it actually all fits together in the big picture. So, all right, so that's all for today, and I will see you guys all next week for our regular class time at 11. So thank you for showing. So we'll see you next week.